We know some of these things from before, so you cannot forget the things we already know about graphing. So these 9 steps will kind of help guide you. So the first thing you want to do, are there any undefined values, places that we know that thing doesn't work? So we're talking about fractional functions might have a vertical asymptote or a hole. Square root functions, have to, the domain has to be where values are greater than or equal to 0. So the first 2 things kind of go hand in hand. We're going to find the values that don't work, then that will lead us to the domain. Next thing you want to do is find the x and y intercepts. Remember, for an x-intercept, you're going to let y equal 0. For a y-intercept, it's easier. You're going to plug in 0, so that's a little bit easier. For number 4, end behavior, we know some things about what the ends are doing. We've explored those limits to infinity. We're going to use that where possible. Remember, a slant asymptote occurs if the top power is exactly 1 more than the bottom, so that could possibly happen. We're going to do the first derivative plus-minus chart using the critical points to help us. Then we can determine number 6, whether they are maxes and mins, where it's increasing, decreasing. The second derivative chart, remember, gives us our concavity where it's positive. It's concave up. Where it's negative, it's concave down. A change of concavity is called an inflection point, so 7 and 8 go together. And then once we have all those pieces, you still may have to plug in some extra points because to show you the exact location of some things. But you want to have inflection points noted, you want to have critical points noted, you want to have the curvature right. So for the very first time, we're going to try to blend all that stuff together. So let's just practice, okay? Let's get all of these things right that we possibly can. Now, if we look at our step number 1 is vertical asymptotes or holes. And there are none for a polynomial, so we know that the domain for this is all real numbers. So we should have a graph that stretches from left to right with no holes, jumps, gaps, asymptotes of any sort. So one thing we can find that's very easy are the x and y intercepts. Now they've been kind to us when it comes to the x-intercepts. That's where the function itself equals 0, and because it's in factored form, then we can just split it apart, and we know we have zeros at 1 and -2. So that part's good. Now let's think about our end behavior. If we were to multiply this out, it is a polynomial whose lead term is x cubed. Now let's explore why it's an x cubed. This one would be an x squared followed by an x. If we were to actually FOIL it all out, the highest power we would ever get is an x cubed. We know that the limit to negative infinity is going to go down and the right is going to go up. So we know what a cubic is doing. So the end behavior left is going to negative infinity and right is going to positive infinity. So now we're ready to look at what are the critical points. So so I can avoid the product chain and all those other things. I'm going to actually physically multiply this out. So if you were to multiply this one is x squared minus 2x plus 1. And then if I distribute it further, I find that lead term we were talking about, x cubed minus 2x squared plus x plus 2x squared. I'm sorry I did this in a really weird way. Minus 4x plus 2. I distributed backwards. I distributed the x and then the 2. Multiplication is commutative, whatever floats your boat. And then we get x cubed minus 3x plus 2. Just check my math, could you please? Does that look good? So I did x That's right, and then I did 2. Yeah, I think we're good. Okay. Now that we have that in a slightly nicer form, let's do the first derivative. So the first derivative is 3x squared minus 3. Now, the critical numbers will be where the first derivative either doesn't exist, and that is a point in the original, or is equal to 0. Well, that's a new polynomial. It doesn't not exist. It exists everywhere. So we just have to look at where that is equal to 0. Yep, so remember, when you inflict a square root, don't forget your plus or minus 1. So what do we know is happening? Well, if we make a plus or minus chart with those values, and I'm just going to plug into the, I didn't factor it ever, so I can just plug right into there. If I plug in some test values, so let's do -2, 0, and 2, into our first derivative, do we get positives, negative? Is it increasing, decreasing? What the heck's happening? If I plug in -2, I get 12 minus 3, which is positive. If I plug in 0, I get 0 minus 3, which is negative. If I plug in 2, I get 12 minus 3, which is a positive. So we know that this is increasing then decreasing. So this should be a local max. And this one is decreasing then increasing. So this should be a local. Now, that takes care of 5 and 6. Critical points, increasing, decreasing, max, and min. So now, so this is our critical points. And this is our plus minus chart of the first derivative. Okay. So now we're moving on to inflection points and concave up and down. That's steps 7 and 8. So now we're going to take the first derivative. We're going to do it again. We're going to do the second derivative, which is just 6x. So 7 and 8 go together. If we do a plus minus chart there, the only point that is of any change is 0. And if we plug a negative into it, that's like -1, we get a negative. If we plug in +1, we get a positive. And so this is a point of inflection because we have changed concavity from negative to positive. So make sure that when we draw our graph, it has to have a concave down, cup is down to 0, and then our cup is up on the other side. So you've got to make sure you show that. So what points do we know? Well, we know in the original we had zeros at 1 and -2. Those were our x-intercepts, which I forgot to do, our y-intercept. If you plug 0 into it, the original is the points on the graph, we get -1 squared times 2, which is 2. So now let's put some of this stuff on our graph paper. So we have some points we know for sure. We have an x-intercept of 1, an x-intercept at -2. We have a y-intercept at +2. Now, we found points of inflection. No, I'm sorry. We found maxes and mins happening at 1 and -1 right here. So we already know 1 gave us 0, but let's plug in -1. And then there's a point of inflection at 0. We already plugged in 0 and got 2. So that's a change in concavity. If we plug in -1 to the original, we get -2 squared, which is 4, and then -1 plus 2 is 1. So that's 4 times 1, which is 4. So at -1, we are at 4. Okay. Now putting all the pieces together, I want to see the concavity the increasing, decreasing, and all that stuff. So we should increase up to a value of x being -1. We should decrease until +1. There should be a change in concavity at 0, and then we should, we'll put all those together. Okay. So far we know for sure that it has to be concave down to there, and then it's going to be concave up. And because x minus 1 is a 0, it's concave up because we know that the right side goes up and the left side goes down. So that should be what our graph is. And then just make sure you have everything on there, okay? So our domain is all real numbers. We had a 0 at 1 and a 0 at -2. We had a y-intercept of +2. It was increasing, decreasing, increasing. It was concave down, followed by concave up. And we have everything involved that we need. And if you needed more points, you could plug in more points, definitely, to the original function. So if this didn't give you enough information and you wanted to plug in maybe a point past 2 and a point -2 and a point past +1, you can do that. Does everyone see how all those things went together? Are there any questions about example 428? Okay, let's look at example 429. Now for the first time we have a rational function, so it has some problems with it. We did these last year. We did these at the beginning of this year. What we're doing now, the change is we're going to be able to show more of the curvature. Hopefully we'll show how all the pieces and parts go together. So the first thing we would look for is what are vertical asymptotes or holes. A hole occurs when it's in factored form and there's a factor on top that matches the factor on the bottom. When in factored form, this is 1 plus x, 1 minus x on the bottom. No factor on top matches the factor on the bottom. There are no holes. But our vertical asymptotes occur when 1 plus x equals 0 and 1 minus x equals 0, which is at -1 and +1. So we know there's a vertical asymptote at -1 and +1. So when we discussed rational functions in the past, my suggestion is put those on post haste. First thing. So at +1 and -1, we have a vertical asymptote. Now this function exists everywhere else, so there should be a curve in the center piece. There should be a curve here and a curve here. There should be 3 curves to the graph. Also, there should be in the domain 3 pieces. I go from -infinity till the first asymptote, leap across it, to the next asymptote, leap across it, keep going. So you'll notice how our domain is in 3 pieces. Our graph will have 3 distinct pieces. So it might have like a swoop, then a swoop, then a swoop. I mean, I don't know. You know, it could be down here and up here, but there's going to be 3 distinct pieces that fill those regions. Now, let's talk about the end behavior. If the power on, I'm one step ahead, we'll come back to number 3. Let's talk about the end behavior. If the power on top matches the power on the bottom of a rational function, we use the coefficients. So the horizontal asymptote occurs at 1 over -1 or -1. Now, can we cross over that horizontal asymptote? Definitely. Is that going to happen? Maybe. I don't know. But when I put on the horizontal asymptote, I only put it on the end pieces. So I usually only will show it over here and here, because usually these are the ends that are going to follow it. This middle piece might completely violate it. I have no idea. So I tend to just kind of go, oh, that's my left and right end. Now let's go up to number 3. Let's go to our x and y intercepts. The x-intercept is where the function equals 0. A fraction equals 0 where the top equals 0. So where does x squared equal 0? At 0. So we hit the x-axis at 0. The y-intercept, you got to plug in 0. So for our y-intercept, just plug in 0 and see what the heck you get. You get 0 over 1, which is also 0. So if the x-intercept happens at 0, that will also be your y-intercept. Now, unfortunately, we have to find critical points. Is it increasing, decreasing? Steps 5 and 6. This, I would keep it in the original form, and let's do the quotient rule. So the derivative. Now, here's where you guys, I noticed, mess up sometimes. Remember, right down the bottom. It's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. You have to start with the bottom. So it is the bottom, keep it in parentheses, times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. Now, usually some things cancel with these. It's just the nature of them. So let's mess with this top here. If I distribute the 2x to both of those, I get 2x minus 2x cubed. And then when I distribute that, I get plus 2x cubed. And so I get, that's a square. And then I get on top that the 2x squareds cancel out. So I get 2x over 1 minus x squared. Now we still have positive 1 and negative 1 are undefined values, but they didn't work in the original because there's vertical asymptotes there. They're not going to work in this. When we make the plus or minus chart, we include them, but as open circle values, they don't work. They just don't work at positive 1 and negative 1. So critical points are points where the first derivative equals 0 or is undefined and they're points in the original. Well, plus or minus 1 are just points that don't work. So where is that going to equal 0? Well, 2x equals 0 at 0. There's no other places that are critical points. The only critical point that might be a max or a min is 0. Now, on the chart that we're going to make, I am going to include negative 1 and positive 1 just as open little circles to remind me, hey, there's nothing there. There's nothing there. But I will include 0. It is a critical point because it works back in the original and it works in the first derivative, but it's giving me a 0 first derivative. So we've got to plug in some points. Where's increasing, decreasing? Is there a max and min? Well, if you plug in, let's plug in negative 2, negative a half, positive a half, and positive 2. We're going to plug them into the first derivative because we're seeing where the first derivative is positive is it increasing, whereas the first derivative negative is it decreasing. What the heck's happening? Well, if you plug in negative 2 to the first derivative, you get negative 4 over something squared, so it's negative. And then if you plug in negative 1/2, you get negative 1 over something squared, so that is a negative. And then if you plug in positive 1/2, you get a positive over a positive, which is a positive. And then if you plug in 2, you get a positive over a positive, which is still a positive. So let's think about what's happening. This whole section is decreasing. So if I were to guess, this is how it could be decreasing and still follow the asymptotes. So I'm assuming it's probably concave down, decreasing right there. That's my guess. How could this section be decreasing and increasing? Well, if this is a local min, that means it would decrease to it and increase. So if I were a betting person, I would bet we have a piece like that, right? Because that's the only way we could decrease. That could be a minimum, and then we could increase again. And then this is an increasing piece, so I would assume it's going uphill. So I'm assuming this graph, without doing any pieces, it's probably going to look like that. Here's where plugging in some points might help. So now we're on to 5 and 6 is done. Now let's do 7 and 8. we have to take this one and do the second derivative, unfortunately. So we're going to do bottom times the derivative of the top minus the top times the derivative of the bottom. Okay, so the bottom's derivative has a chain rule component. We're going to drop the 2, leave it alone. Power goes down by 1 times the derivative of the inside. All over the bottom squared again. So now it's going to become the 4th. Now, the bottom is always positive. The bottom has forced us to still have those undefined points at positive 1 and negative 1. The top. I'm going to factor out a 1 minus x squared. There's a 1 minus x squared here and a 1 minus x squared here. So let's take that out. What's another thing they both have? I noticed there's a 2 here and a 2 here. So let's take out a 2. I'm just trying to make what's left as simple as possible. So if I took out one of them here and a 2, I'm left with just one of those quantities. Now I took out one of these and the 2, so all that's gone. So you see how you're just left with a negative 4x? And then we got negative 4x squared. Thank you. I caught up with myself. Okay. I'm going to leave it in factored form because the factors are going to help me. There's something that's going to happen too, just a second, and I'll tell you. See how there's 4 of these down at the bottom, but there's one of them up here. Let's cancel one from each of those. What should happen in a rational function is the power should go up. If you simplify it correctly, the power in the denominator should go up by 1 every single time. So do you see how in the first one it was one of those to the first power, and then it became one of those to the second power when it was all reduced down, and now it became one of those to the third power. It should continue that pattern. What does that give us? Well, that gives us that we have still our undefined points at positive 1 and negative 1. Undefined points at positive 1 and negative 1. Okay, so when we make our plus and minus chart, positive 1 and negative 1 are only on there just because they don't work. So they cause that gap, that weirdness. But they're nothing important other than that. They should show up on every graph because, or on every chart because of the fact that they're vertical asymptotes. Now, 2 is never going to equal 0, but where does 1 minus 3x squared equal 0? Well, if you solve that, you get that you have to square root, which I didn't do, I said, that's plus or minus the square root of 1. Now, you can rationalize if you have the urge. That's square root of 3 over 3. I don't care. We just need to know approximately where that decimal value is located. So if you take the square root of 1/3 and you get a decimal value, this is approximately, because we have to put it on a graph, plus or minus 0.58. It's 0.57735. Yeah. Okay. It's a funky gross number. So let me make my chart just a little bit bigger. And I'm going to include now negative 0.58 and positive 0.5, because those are possible, what are they called? And let me draw. Those are possibly points of inflection where the concavity changes. So negative 1, we have a gap. Something happens at negative 0.58. I'm going to abbreviate it a little more just so it fits. And positive 0.58, Now, these points work in the original. They work in the first derivative. They work in the second derivative. They're just points. But the concavity is going to change at those points. Okay. Well, maybe. They might change. We're going to find out. Okay. So let's make our plus minus chart now for the second derivative. Now, this is our second derivative. I'm just going to plug in points into the whole thing because it's just going to make it nicer. Okay, so let's plug in -2, -0.80, +0.8, and 2. Now, the symmetry of this, see how the original function is even? This should be symmetric. Whatever's happening to the left of the y-axis, it should also happen to the right. The symmetry of this, it's an even function. You notice when I drew it earlier, I thought that it probably did this, this. See how that's an even function. But let's plug in. Okay, if we plug -2 in, we get 1 minus a bigger number, which is negative, times 2, which is still negative. And then -2 down here is going to be a negative. And then cubits, you're still going to get a negative. So we're going to get a negative divided by a negative, which is a positive. So the concavity there is that it is concave up. And just check that I did that right. -2, so that would be 1 minus 12 and 1 minus 4, which is a negative. Yeah, okay. Now if you plug in 0.8, here's where a calculator is going to help me. Well, if you plug in 1/3, that's going to be 1. 1 minus 1. Okay, never mind. Okay, let's see. Let's plug in 0.8. 1 minus 3 times -0.8 squared is a negative. And then 1 minus 0.8 squared is a positive. So you get a negative over positive, which is a negative. If you plug in 0, you get 1 over 1, which is a positive. If you plug in 0.8, you get a negative. If you plug in 2, you get a positive. So our points of inflection are plus or minus the square root of 1/3, because look, it changed. It changed. Are these points? No, they don't count. Okay, you see these are just a lot of work, these problems. Okay, so we've done 7 and 8. So the last thing is, what are our points? What do we plug in? Okay, so we only really have the 0, 0 point. We don't have much else. Now remember what happens. This is decreasing. X squared. I need to look at something. Okay. So square root of x equals square root of 1/3. So it says there's a change in concavity right there. But I didn't necessarily believe it. That's why I'm looking. Okay. Let's go back. I'm just checking my work here. So that would be 1 minus x squared times 2. And then that would be I'm just making sure it's right, guys. Oh, there we go, look. This is minus x squared minus 4 is minus 5. So I'm like, something's wrong, and I didn't know what it was. That's a 5. I'm so sorry. I can't add or subtract. That would be a 5. That would be a 5. Sorry, this would be the 5. And the square root of 1/5 is 0.4. One little thing can throw this off so bad, and I'm so sorry. Let's go back to our graph. So if we put in 1/5, what does it do? I'm just checking to make sure that I don't have one other mistake. That's the problem with these. You have to, especially the rational ones. You just have to be really, really careful. And when I'm doing these, you know, even I make mistakes too. Let's see if I can find something that might have went wrong. So my first derivative is correct. Decreasing, decreasing, increasing, increasing. So our first derivative chart's perfect. Something's going on with our second derivative. Okay, let's try again. It's got to be my second derivative is wrong. Okay, let's do this one more time. I'm so sorry. We're going to get through 2 problems today. And your homework might just be 2 problems. I'm just letting you know.
Really?
Yeah, I think we're going to do one polynomial and one rational tonight, I think. Okay, let's start the second derivative one more time. Okay, the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom. Okay, so they have a 2 in common, and they have one of those in common. So let's take out a 2 and one of those. So what's left? One of those, and then plus, there we go. There's my mistake. See the 2 negatives here. Okay. So I'm like, that does not match up with what in my brain that graph is doing. Okay, look what happens. One of these cancels with one of those. So we get 1 plus 3x. There we go. I'm so sorry. Okay. 1 plus 3x squared will never equal 0. We get that 3x squared equals -1. There's no points of inflections. But we still want to make a plus-minus chart just so we know the concavity. we have to include negative 1 and 1. And then we just need to plug into this to figure out our concavity. Sorry about that. That little mistake, see what happens? Okay, let's plug in negative 2, 0, and positive 2 into here to see our concavity. So I'm like, something's not right. What did I do? Okay, if you plug in negative 2, you get a positive on top. When you fourth that power on the bottom, oh, we got 3 of those. See, I can't make more mistakes. If we plug negative 2 into the bottom, we get 1 minus 4, which is negative cubed, isn't it? So that's concave. That's what I thought it was. If we plug in 0, we get 2 on the top and 1 on the bottom. That's positive, concave up. And then if we plug in 2 on the top, we get a positive. If we plug 2 in the bottom, we get a negative. Cubic, still a negative. So that's a negative. Okay. So last thing I want to do is I want to write some facts down, and then we'll draw our graph. Okay. So we know that it is increasing from 1/2 to from 0 to 1, and then from 1 to infinity, and then it's decreasing from negative infinity up to negative 1, and then negative 1 to 0. It is concave down from negative infinity to negative 1, and 1 to infinity. It's concave up from negative 1 to positive 1. Now, there are no inflection points. There is a local min at x equals 0. So now we have everything. And now if we put it together, this is concave up. It is decreasing and increasing. I need a point right here. So based on everything I know, it's going like that and like that. And because of the symmetry of it, let's just plug in 1. Because whatever's happening at 1 will also happen at negative 1. If we plug 1 into the original function, we get 1. Oh, we can't plug in 1. Let's plug in 2 and negative 2. If we plug in 2, we get 4 over negative 3. 4 over negative 3 is approximately negative 1.6. And so this one would also be approximately negative 1.6. 1.6. Okay. So you have homework. 2 problems due at the beginning of class tomorrow. I'm going to write them down for you. I'm going to give you, well, you can use you need to do all 9 steps, graph it, make it pretty. Okay. So this is what I want you to graph. I want you to graph in all 9 steps. Those are the 2 functions I want you to do. Okay?
I would have a field day.